Why do we study bounce diagrams? Well, typically, bounce diagrams are studied in the time domain, and they are affiliated with the TDR, time domain reflectometry, because it's just like a radar system where you send a signal and look for the reflections, and from the location of those reflections and the nature of the reflection, you can tell what's happening there. So you can study the behavior of a discontinuity down a transmission line. Actually, it has more uses than that. We use it in device characterization, material characterization, all sorts of other applications that we do with the time domain reflectometry. I'm going to teach you the bounce diagram in both the frequency domain and the time domain. And the frequency domain is more of a mathematical tool for analysis rather than a practical tool for applications. It gets us a solution of a mathematical problem much faster. And it maintains some physical insight of what's happening on it. Well, someone would say, what do you mean bounce diagram in the frequency domain? Although I'm in steady state, I can still watch the waves traveling one way and the waves traveling the opposite way and their reflections. That's frequency domain. Steady state is frequency. Time domain is a transient. What happens when we first kick in the signal, or we have a sudden change in amplitude, or we have a pulse, or a step, or a sawtooth, or what have you. That's time domain. So the frequency domain will be steady state. So all these are harmonics. And I'm monitoring here the waves that go this way and the waves that go that way, and they're all sinusoids. If I look at them on a scope, they are added. You have a sinusoid going this way, another sinusoid going that way, and they are added to each other, and eventually you have a third sinusoid. You can't tell. When you look at the final solution, it's a sinusoid. You won't be able to see this from that. So practically, you're not going to be able to see them apart. But mathematically, here we can see them apart, and we can determine the standing wave ratio, for example, and the individual things that happen, matching. All these are mathematically very useful tools. So what we say is, we have a source and a load, and there is, let's say, an initial signal, not an initial in terms of t is equal to 0, all right? One of the waves that travel that way, let's just monitor one of them, okay? And that wave, I'm just going to call it V plus, although it's not really absolute V plus, I actually called it A. Let's follow that notation. Just one of the waves that travel that way. That wave is A. Okay? And that wave is harmonic. That's a phasor, A. And by the time it moves to here, it's going to be A e to the minus gamma Z. By the time it reaches here, it's going to be A e to the minus gamma L. Okay? And that wave is going to hit this continuity, and it's going to reflect back. So you have A e to the minus gamma L times the reflection coefficient gamma sub L. That's your reflection coefficient. And that wave is going to travel this way. And when it comes to here, it's going to be the same quantity here. I'm not going to keep writing that. And it's going to be e to the minus gamma, this distance here, d. And by the time it reaches here, it's going to be the same quantity here, which is between brackets or parentheses, e to the minus gamma L. It moved the distance L, so it gets attenuated by e to the minus alpha L, and the phase will change by e to the minus j beta L, so it's e to the minus gamma L. It hits a source and reflects again. And I'm going to put this between square brackets. So I have the square brackets times e to the, times gamma at the source, gamma S. There's a reflection of the source. I'll call it gamma S. and this quantity here moves and it gets here, so it is the square bracket times gamma s e to the minus gamma z. When it reaches the load, it will be the square bracket gamma s e to the minus gamma l. Right? And I keep doing that. Again, it reflects again. And if I put this between wiggle parentheses, so I have gamma L times wiggle parentheses, and so on and so forth. So basically, I can represent it by a bunch of waves going back and forth, and I can write those expressions. It's an infinite series, right? It's a steady state, so this is going on indefinitely. The wave that travels to the right is some of these. If I do a sigma here, I get, guess what? I get V plus e to the minus gamma z. If I add those, I get V minus sigma here, equal to V minus e to the plus gamma z. All of these are components of the V plus, and all of these are components of the V minus. All right? And if you read this addendum in the chapter, you will see the expressions here, and you will see the series summation. It's a geometric series, by the way, okay? And if you do the geometric series addition, okay? By the way, here's the definition of gamma S and gamma L. Gamma L is ZL minus Z naught by ZL plus Z naught, right? How much is ZL mismatched with Z naught? And gamma S will be the mismatch between ZS and Z naught. Okay, so here's the expressions, and where's the summation of the series? Come on. Okay, here's the series at the source end, in the middle, at the load end, and down here is the phasor series, the expression here, and on the right side is the sum. Okay, you can see the sum of the series here. And I have some notation here that I'm using gamma L and gamma S, and T is used for e to the minus gamma L. I'm calling that T. And the A, which is the initial A here. Okay. And I'm showing you that eventually you can relate all that to the V plus and V minus, and you can have a solution for the boundary condition at the A. Is that the end? Yes. All right? Now, why is this a good tool? Basically, if you master this one here, you can, if you have say a cascade of several discontinuities. If you write the solution for this, gets too complicated. While if you do a game like that, you can see things much faster and easier. So instead of sitting down writing all these boundary conditions, this tool here can solve these kind of problems much easier. All right? Now, next time we'll do the time domain bounce diagram. Any questions before we go? So please read that chapter and let me know your thoughts. And